Okay, I guess we can get started. So good morning, good afternoon, and good evening, everyone. My name is Qiao. I'm a faculty from Xiamen University, China, and this is the third meeting of this year's SIGCOMM Paper Reading Group, or this season's SIGCOMM Paper Reading Group. And in total, this is our 20th meeting for now. So time really flies. So in this meeting, we are honored to invite Dr. Chen and Dr. Wenxue to join us as guests of honor to study their paper revisiting RDMA reliability for lossy fabrics. And this paper won the Best Student Paper Honorable Mention at the SIGCOMM 25 last month in Portugal. And as the title of the paper suggests, this one mainly focuses on how to make lossy RDMA networks to be efficient and with high performance and also with reliability, of course. And since this is an educational initiative, so for the first part of the meeting, we will have Yunxue, a graduate student from Xiamen University, to present this paper as a good exercise for her. And in the second part, Wenxue and Kai, we can have a discussion, and in the meantime, we'll take questions from the audience for the during the second part of the meeting. So I think without further ado, I want to thank Wenyun and Wenxue and Kai to taking time to join the meeting. But now I think Wenyun, you can get started. Thank you.
Okay, thanks for the opening. Hello everyone, I'm Wenxue from Xiamen University. Today I will share the paper called Revisiting RDMA Reliability for Lossy Fabrics. This is a joint project between HKUST and Huawei. Before we start the main discussion, I'd like to briefly explain several key concepts that appear throughout the paper, so everyone can follow the later sections more easily. First, RDMA, or Remote Direct Memory Access, is a networking technology that allows one machine to directly read or write another machine's memory without involving the CPU. This enables extremely low latency and high throughput communication, and is widely used in modern data centers. To make RDMA reliable, traditional systems rely on PFC, Priority Flow Control, and CBFC, Credit-Based Flow Control. These mechanisms prevent packet loss by parsing traffic or by tracking available buffer credits. However, they also cause serious issues, such as head-of-line blocking, congestion spreading, and even network deadlocks. The hardware that implements these mechanisms is called an RNIC, short for RDMA Network Interface Card. It offloads RDMA transport logic from software to hardware, achieving much higher performance but also constraining protocol flexibility. Next, let's talk about ECMP, or Equal Cost Multi-Pass Routing. This is a load balance technique that splits traffic across multiple network paths with equal cost. In other words, instead of sending out packets through a single route, ECMP distributes packets across multiple paths, which improves link utilization and reduces congestion. Together, these concepts form the foundation of TCP's design and help us understanding why we revisited RDMA reliability for Lossy network. First, I would like to introduce the landscape from lossless RDMA to lossy RDMA. As shown here, around 2015 to 2016, almost all data centers adopted lossless RDMA solutions. This system relied heavily on PFC or CBFC to ensure a lossless underlying fabric. In practice, this means that whenever congestion control occurred, the network would parse the traffic to prevent packet loss, effectively guaranteeing reliable delivery. Meanwhile, the RDMA NICs use a simple go-back-N retransmission mechanism, which worked well under ideal lossless conditions. However, the deployment scale of lossless RDMA networks is restricted. The reason is that the link level flow control, for example, PFC or CDFC, causes several performance issues, like head-of-line blocking, congestion spreading, deadlock, and significant switch buffer overhead. Because of these problems, the deployment scale is limited. Therefore, since 2018, both industry and academia have been exploring efficient RDMA transmission over lossy fabrics. Up to now, almost every leading company has its own customized lossy RDMA solution. The state-of-art lossy RDMA solution called RNIC SR implements a simplified selected repeat mechanism, or selected repeat for short, in RNICs to enhance the loss recovery efficiency. However, even with RNIC SR, performance issues persist in lossy fabrics. First, RNIC SR assumes single pass transmission with ECMP as the default load balancing scheme. However, ECMP hashing collisions are unavoidable and they cause significant throughput degradation. The impact is especially pronounced in today's AI workloads. Meanwhile, packet-level load balance methods such as adaptive routing are promising alternatives to ECMP. However, RNIC SR is natively incompatible with packet-level load balance. The root cause of this incompatibility is that packet-level load balance can cause out-of-order packet arrivals, even when there is no packet loss. While RNIC SR assumes that all out-of-order packets are due to packet loss. As a result, combining packet-level LB with RNIC SR leads to excessive spurious retransmissions, significantly degrading throughput. For example, if P4 arrives before P2 and P3, the receiver will request the sender to retransmit P2 and P3. Second, certain lost packets cannot be recovered through fast retransmission in RNIC SR. Specifically, the RNIC SR requires a SUC to trigger the loss recovery mode. As a result, if the tail packet of flow is lost, no SUC is generated. This prevents recovery through a faster retransmission and instead relies on a retransmission timeout, or RTO for short. Additionally, to avoid retransmission ambiguities, the sender enters the loss recovery mode only once and remains in this state until it exits. The sender exits loss recovery mode only when it receives a packet with EPSN greater than the largest PSN of outstanding packets prior to entering the loss recovery mode. As a result, if the retransmitted packets are dropped again, they can only be recovered through an RTO. The increase in RTO events could significantly degrade the performance. Both issues fundamentally stem from the assumption that packet order is preserved, which is no longer valid under modern load balance schemes or high bandwidth lossy networks. Based on the above analysis, the paper aimed to revisit RDMA reliability to meet the following requirements. First, independence from PFC. The proposed solution must eliminate the dependence on PFC to completely avoid its associated drawbacks. This requires the ability to efficiently handle packet loss in Ethernet-based data centers. Second, compatibility with packet-level LB. RNIC SR suffers from significant spurious retransmissions when combined with packet-level LB. The proposed solution must be inherently compatible with packet-level LBs, which necessitates the accurate distinction of real packet losses from out-of-order packet arrivals. Third, the ability to quickly retransmit any lost packet. Unique SR often fails to recover certain packet losses via faster retransmission, leading to excessive RTOs. The proposed solution should enable prompt retransmission for any lost packets. This necessitates an explicit loss notification scheme. And finally, a hardware-oriented design. While software solutions can bypass hardware resource limitations due to the greater resource availability in software, they cannot leverage unique offloading compatibilities and face inherent performance limitations. Therefore, the proposed solution should adopt a hardware-oriented design, ensuring minimal memory and computational overhead. The paper proposed DCP, a transport architecture consisting of DCP RNIC and DCP switch. Conceptually, DCP defines the data plane, DP for short, for payload transfer, and the control plane, CP for short, for header transfer. While lossless RDMA ensures that both DP and CP are lossless via PFC, DCP switch only ensures a lossless CP while allowing the DP to operate in a lossy manner. The key idea of DCP is to leverage the lossless CP feature to enhance RNIC's reliability, mainly in packet retransmission, packet reception, and packet tracking. This table summarizes the difference between DCP and its closely related works. DCP is the only one that fully meets the four requirements. First of all, I would like to talk about the lossless control plane. DCP switch implements a packet trimming mechanism similar to the previous works. Specifically, when there is no congestion indicated by a relatively low queue length, the entire data packet is enqueued into the normal queue, also called the data queue. When the data queue's length exceeds a given threshold, the switch trims the payload from the packet and goes to step 2. In step 2, the switch modifies the DCP tag in the remaining header and includes the header only, or HO for short, packet into another queue, also called the control queue. To ensure lossless CP transfer, this switch uses a weighted round robin of WR for short scheduler to prioritize the control queue. By configuring WR weight properly, DCP can guarantee that the control queue remains lossless. Then I want to talk about how can DCP utilize the HO package for loss recovery. Let's first consider a straightforward HO-based retransmission solution. Upon receiving an HO, the sender side RNIC fetches the corresponding WQE and processes it, then fetches the data and finally encapsulates the data to a packet. This idea is simple to come up with, but it has two issues. The first issue is inefficiency retransmission. It requires 2 PCIe RTTs to finish a single packet, which is quite inefficient. The second issue is incompatible with the congestion control model, or CC for short. Since HO packets are stateless and independent, if we immediately retransmit upon receiving an HO, the transmission rate becomes tied to the arrival rate of HO packets. Therefore, DCP proposes an efficient HO-based retransmission approach. The paper incorporates a retransmission queue, or retrans queue for short, in host memory for each QP on the RX path. Upon receiving an HO packet, the RNIC extracts some metadata from HO, packaging it into a retransmission entry and writes this entry. Actually, it's a data structure into a corresponding QP's retrans queue. Note that this retrans queue is exclusively managed by the RNIC, so this does not involve any software overhead. In the TX path, the author employs a benched fetching approach. After checking whether the retrans queue is empty and getting value from CC, the RNIC fetches multiple retransmission entry and WQEs from retrans queue and SQ respectively. After performing address translation, the RNIC fetches and encapsulates multiple packet payloads and finally updates the CC state. So in summary, the approach improves the PCI utilization and enables CCs to controlling on the retransmission rate. Now, since load balancing can lead out of order packet arrivals, the question is how to handle them. A feasible way is to allocate a very large reorder buffer in the RNIC or in the host, where the out-of-order packets are temporarily stored. Once all packets are received, the RNIC or the host reorders them and push them into application memory. However, this approach introduces significant memory and CPU overhead. To address this issue, the team chose to extend the standard RDMA header, allowing the RNIC to write all packets, whether order or out of order, directly to the correct locations in application memory. This eliminates the need for a real buffer. This kind of header extension is a kind of common approach adopted by many protocols, such as FileSyn and so on. Another question is that how to track which packets have been received or lost. Usually people use packet level bitmaps. However, bitmap introduces trade-offs between memory overhead and processing efficiency. One approach for maintaining bitmap is to pre-allocate a fixed length, typically BDP-sized bitmaps for all active QPS. This method has constant packet processing latency, which is good, but its memory overhead is high and it often wastes lots of space. Another common approach is the linked trunk method. Each QB is pre-allocated with only one trunk and is linked with additional trunks as needed. This approach improves memory utilization. However, as the out-of-order degree increases, accessing latency also grows. This is because accessing a bit in the inner trunk requires n steps. So this paper proposes a bitmap-free package tracking approach to break the trade-offs. It's based on the exactly once feature on the HO-based retransmission. Ensures that only lost packets are retransmitted. So for any given packet, exactly one copy arrives at the receiver. Based on this feature, the receiver side DCP RNIC tracks message level information using package counting rather than tracking at the packet level. It maintains a multi-bit counter for each message. Upon arrival of a packet, the corresponding message counter is incremented by 1. When the packet counter equals the max size, the receiver determines that this message is complete. Note that this exactly once assumption may be violated due to the link failure or accidental HO package losses. To handle these extreme cases, the paper developed a customized timeout approach as a fallback. Finally, I would like to talk about the combination of design models. Ideally, all of the design modules should be used together. However, it's important to note that this bitmap-free package tracking relies heavily on the exactly once feature. Therefore, in environments with very frequent failures, this approach may not be suitable. In fact, this bitmap-free design is also orthogonal to the rest of DCP RNX architecture. This means traditional packet-level bitmaps combined with the remaining components of DCP RNIC also function correctly. This paper implements the lossless control plane using the Phono-2 switch and build a fully functional prototype of DCP RNIC using an FPGA board. They implement DCP RNIC by modifying specific modules based on an FPGA-based RNIC GBN baseline prototype. This paper evaluates the basic performance of DCP prototype. It successfully maintains hardware offloading capabilities, achieving throughput and latency comparable to RNIC GBN, both of which significantly outperform TCP. They conducted extensive tests by experiments. The test bed is shown here with 2 Phono switches and 16 servers. They use several benchmarks to demonstrate that DCP achieved superior loss recovery efficiency. DCP is natively compatible with adaptive routing, or AR for short, in the experiments. And DCP provides benefits for AI workloads. DCP reduces the GCD of all reduce and ultra-out by up to 33% and 42% respectively. They also conducted comprehensive simulations. The topology is a 2-layer CIOS network with 256 servers, and all links operate at 100 bps. We validated that DCP achieves a larger improvement in cross-DC scenarios, even with relatively small switch buffers. In contrast, the lossless solution requires much larger switch buffer and still perform poorly. This paper also shows that DCP benefits from CC and high-loss scenarios, and that DCP plus CC achieves the best performance in these cases. Finally, they compare DCP with ARC-TLP and timeout-based solutions and show that DCP outperforms it. Finally, I would like to make a conclusion. In this paper, the authors team present DCP, a transport architecture that rethinks RDMA reliability for lossy networks. By leveraging a lightweight lossless control plane in switches, DCP enhances the RNIC's reliability, enabling compatibility with packet-level LB, process retransmission, and minimal memory and processing overhead. The prototype and evaluation shows that DCP significantly outperforms the existing RDMA solutions, advancing the practicality of high-performance RDMA over lossy fabrics. That's all. Thanks for your listening.
Okay, yeah, thanks Wenyun for the presentation. I think it's pretty comprehensive. I think it really conveyed the key ideas of the paper. So now that we finished the presentation, I've been taking notes. So I will talk to Wenyun later about some part maybe we can improve in the future presentations. But I think we can start the discussion part. So for all the audience, if you have any questions, you can just unmute yourself and speak. Or if you feel it a little bit too shy, you can also type your questions in the chat channel, which I will monitor. So while we are waiting for other for all the participants' questions, I'd like to ask a couple questions to Wenxue and Kai. So the design of I think I'm not an expert in RDMA. I have some knowledge about that, but I think that the design of header-based, header-only based retransmission is essentially, I think it really reminds reminds me of NDP, right? From I think from 2017, yeah, or from SIGCOMM 2017. So for that part, I think Wenyun, can you go back to the slide where you compare the slide you compared with different related work about what features or what requirements we have. I think in the earlier part of the presentation, there's a slide showing we have four design requirements, right? And I think there's a table listing all of many related work and try to compare. So what's the fundamental difference between DCP and NDP? Yeah, this yeah, slide number 20. Yeah. Slide number 20, please.
Oh, it's a little slow. Oh, I will write it in the slides 20.
Okay, cool. Wenxue, can you hear me?
Yeah.
Okay, yeah, I'm asked, but basically my question is the design of header only retransmission is, I think to me it's very related to the design of NDP, right? I think in NDP they also use to trim the data payload, right? So what's the key difference here?
Okay, actually both NDP and CP, this citation 26 and citation 18, both utilize the packet trimming function in the switch, and CP also use this trimmed packet is header to do loss recovery, and NDP is more related or designed for a receiver-driven CC. So NDP use the trimmed header in the receiver to estimate the receiver bandwidth because the packet is actually it's actually not lost. Its header is still be transmitted to receiver. So receiver has the whole view of the congestion condition. For example, if the receiver receives more head only, it can think the network is more congested. So the receiver can use this whole information to do a better receiver-driven congestion control or sending rate estimation. So that's the main parts of NDP, and actually DCP is more likely to CP because we both focus on loss recovery. And the difference between DCP and CP is CP is CP's end host is software, but DCP's end host is RDMA NIC. It's totally hardware design. So in our detailed design, not only the HO-based retransmission, but the BMS3 packet tracking and the extended RDMA header is both is all designed for RDMA scenario. So in CP, actually it didn't mention a lot about his end host design because based on the head only, do the loss recovery using in the software is very straightforward. It can just maintain the whole HO packet in its host memory because host memory is very sufficient. But in our design, the RDMA NIC as RAM limit is the biggest problem. So we cannot maintain many information in the RNIC. So for the HO-based retransmission, we consider to introduce another, let's say, RDMA structure, the retransmission queue, aside with the original sender queue, receiver queue, and the completion queue. this retransmission queue is located in the host memory and is created when the connection is initialized. So when RNIC receives the head-only packet, it can get some metadata from the HO's field and directly write this metadata into the retransmission queue into the host. So when the RNIC enters the transmission state, it can fetch some retransmission entry from the retransmission queue and execute the retransmission process. So this detailed RDMA related design is not mentioned in both it's not mentioned in either CP or NDP. So I think that's the whole that's the primary difference between DCP with them, because they are both designed for software in the host, and we designed for hardware in the host. Yeah.
So yes, following this line of questioning. So sorry, I may sound a little bit too amateur regarding this area, but you mentioned that like neither NDP or CP leverage perform any implementation in the hardware. So basically, in particular, in the end, at the end host is the software-based implementation. So is it possible that no, let me rephrase my question. So how, like I don't know, you I didn't fully finish your paper finish your paper, but in your experiment I assume you did some like a macro benchmark to do a little bit breakdown analysis about which part brings you like the most gain in terms of performance. So how big of the impact of hardware based and host implementation plays into the overall performance improvement?
Oh yeah, that's a very good question. Actually, we compare DCP with TCP. TCP is the default network stack used in software, and for the throughput for the throughput for a single flow, both DCP or the commodity RNIC, for example, Connect X5, both DCP and RNIC can achieve about 50% higher bandwidth than TCP. So actually, software network stack implementation is actually inefficient, less inefficient than hardware network stack, both in throughput and latency. For the latency, DCP also achieves about 2 times less latency than TCP.
I see. So because I based from the paper, actually from the legend of your experiment result, I didn't see the comparison with like NDP or CP. So did you by any chance did any comparison with them? Maybe not including the paper, like because if we simply look at the table here in this slide, right? In terms of support the first 3 design requirement, I think it's I say independence from PFC and compatible with per packet load balancing, as well as fast transmission. Both NDP and CP, they support those features, but maybe to different type extent of performance. So did you compare DCP with these two? Like how much improvement we can get from comparing with these two?
Yeah, okay. Actually, we didn't compare DCP with both of them because we didn't find its testbed implementation. So if we have to compare with them, we have to re-implement this system in our test lab. So it's a relatively high overhead. So we didn't compare with them, but we think its performance is comparable to TCP because they are software implementation, so it's very hard for them to achieve better throughput than the baseline TCP. Yeah. I think your question is, what's the difficulty to implement the DCP, NDP or CP's design in hardware?
Yeah, something like that. Yeah.
Yeah. I was asked with this kind of like question. My thinking is actually, if you plan to re-implement the similar design in hardware, you are actually proposing a new architecture design. So that's the process. That's a process during during which DCP is proposed. DCP is refined step by one step based on the RDMA. RDMA's unique architecture feature and its RDMA unique limitation. So in the beginning, we actually want to say how hard to re-implement NDP and CP, and we actually found that it's already a new design or an architectural revising if we do this. Yeah.
I see. Yeah, I think that makes sense because if if you try to implement NDP or CP in hardware, you are spending too much effort trying to improve an existing solution instead of proposing your own design.
We have to revisit the RDMA unique architecture and introduce some new necessary module, for example, the retransmission entry, and to improve the data path efficiency. For example, when in our HO-based retransmission, we use the batch fetching to improve the retransmission data path. So that's this design were proposed one by one to finally improve the performance and to finally fill the overall architecture. So yeah, that's the process.
I see. Yeah, I understand it better now. Okay, cool. So my next question goes to, I think there's a experiment. Basically, you try to evaluate DCP in like an inter-data center scenario, right? It's relatively long distance DCP. Wenyun, can you go back to that slide in the evaluation part? Wenyun, can you hear me, Wenyun?
Oh,
yeah,
yes,
okay.
Please wait a minute.
Sure. I think it's probably slide 49 or 50 or something.
Is this right?
Next page. The simulation experiment. It's 50.
Sorry.
Page 50. Yeah.
Oh, sorry, it's a little slow.
Yeah, it's okay. I think mainly that's the internet issues here. So
yes, this page.
Oh no, sorry.
The simulation page.
Oh,
maybe
it's
50,
page
50,
50. Yes,
50 or 53. I forgot.
Is this right?
53.
53.
Yes. Wait a second. Yes.
Okay.
Yeah. So okay, there we go. So in this part, you essentially so I would imagine, so in cross data center scenario, that essentially you might need the traditional design or the default PFC or the default DCQC. Essentially you would need a larger buffer. That's a key issue. Is that the most fundamental issue in the long distance scenario?
Yes, for the lossless solution, it has to maintain an efficient, a very large headroom to make sure the in-flight packet between last hop and this device lossless, because the lossless solution relies on PFC to ensure no packet loss. And PFC, when PFC detects there is a growing Q length in this device, it will generate a port frame and transmit this port frame to the upstream. So the upstream will stop transmission. However, during the propagation of this port packet, there may be some in-flight packet. They are already in the pipe in the path between this hop. So we have to reserve a large buffer for this in-flight packet. And if the length of this one hop is very long, the one hop BDP, bandwidth delay product, may be very large. So we have to reserve much more buffer for this long distance communication. So in this experiment, because we evaluate the 100 kilometer and 1000 kilometer, so we have to increase the headroom buffer size for these lossless solutions. For example, we actually expand or enlarge the switch buffer size for this lossless solution and we allocate a very large headroom for the PFC to work. However, for the lossy solutions, for example, our design DCP or the another lossy solution RRN, we still use a normal switch buffer 32 MB. So even the lossy solution use a very little switch buffer, the lossy solution still achieves better performance. Yeah, that's the problem in the long distance transmission. Lossless solution may experience very low switch buffer utilization because the port frame need a long time to arrive at the upstream. So the upstream may and after the port frame, the downstream device have to generate a resume frame to notify the upstream device to restart the transmission. And because the propagation delay is very long, so the upstream device may have to wait a very long time to restart. And during this period, it may experience low utilization. The bandwidth, the link capacity may experience low utilization. Yeah.
That explained in the top two figures. I assume the last one is for 100 kilo and the right one is 1000 kilometers, right? The top two figures, right? So essentially with longer distance, the performance of the other three solutions essentially getting much worse. But as we can observe that the design of TCP, essentially the slowdown rate is relatively stable, right? Less than 10, I think. So I think that's that's really promising, given that now we are essentially trying to move a huge amount of data across different data centers. I think that's a very good result. Yeah.
Yes, actually, Lossy solution are more friendly for long distance transmission, not only DCP but also TCP.
I see. Yeah, but still, I think we already established that DCP performs very well. But just out of curiosity here, so multipass RDMA in these two figures, in particular in longer distance, multipass RDMA essentially performs much worse. But PFC, the lossless solution, actually essentially the red line, the PFC, the default solution, and when compared with IRN, there's I mean, the performance difference is close. So what's the reason for that? And especially in certain cases, the performance of IRN is even worse than PFC. Have you analyzed? I know that those two are not your design, but I'm just curious what could happen, or what could lead to that result.
You mean why RN sometimes performs
worse than PFC? Yeah.
Worse than PFC. I think the problem is that PFC's performance is unstable in long distance transmission. Because as I mentioned earlier, we enlarge the switch buffer for PFC. So in sometimes if the transmission works very well, no PFC pulse frame is generated. PFC works very perfect because there's no pulse, and the upstream device will not stop transmission. So it is continually transmit packet, very stable. So in this case, PFC works very well, and sometimes if the pulse is generated, PFC performance degrades significantly. So I think PFC performance is unstable. It's because sometimes some flow didn't experience PFC pulse, but sometimes some flow experience them. So that's the reason this PFC line is very unstable. So by average, the PFC performance is worse than RRN. I think it's straightforward, because lossy solution is more friendly in lossy scenario. In long distance scenario.
I see. Okay. I think there's a question from the other audience. Chen Xingji has a question. Essentially, which CC algorithm was used during this experiment? I know the answer, but I don't know the second question. Do you think performance of DCP can be different under different congestion control algorithms?
Okay, so the CC used during the experiment for DCP is DCQSN, because we actually reuse the commercial RNIC, and the built-in CC algorithm is DCQSN. And in our all simulation and test bed experiment, we all use DCQSN to maintain a consistent result. And do you think performance of DCP can be different in different congestion algorithm? I think it might be different, but the performance advantage should be. I think the performance advantage is consistent. because as shown in this page, RRN has its own congestion control algorithm, and MPRDMA has its own CC algorithm, and the DCP outperforms them significantly. So I think the CC algorithm is not very important in our experiment. Yeah, that's
so
my.
Essentially, so essentially, you're saying that from your best guess, essentially the design of DCP, the DCP does not rely on any particular congestion control algorithm, but instead,
Yes.
due to its this data plane and control plane partition or separation design, it actually could for different congestion control algorithms, if we running on this on these DCP fabrics, it actually can perform you expect them to consistently perform better, right? That's your guess.
Yes, because DCP focus on reliability, focus on how to improve the loss recovery efficiency, and the congestion control is in another level. Congestion control is to controlling the failure rate, but not for loss recovery. So DCP is actually compatible with any CC algorithm. In its architecture, DCP is decoupled with the CC module.
I see. Cool. So David has another question. Yeah, thanks, Zhenxing, to you too. So David's question is, he also wants to follow up on our earlier discussion about regarding NDP. So he's wondering, how do you see the role of UEC and the DCP play in future data centers? And if there's a way that the DCP can benefit from the standardization effort?
Yeah, thanks. That's a very good question. Actually, DCP is inspired. DCP was inspired by the UEC because UEC mentioned in its specification that it includes a packet trimming function in the switch, but UEC didn't mention how to utilize the packet trimming function for the RDMA NIC. So we are inspired by UEC, and we are trying to think how to actually utilize this packet trimming function for the RDMA network. So that's so we designed DCP. I think DCP can benefit from UEC because if some future UEC ready switch already support the packet trimming function, we did in these cases DCP will not require the modification to switch. So DCP will only to support customized RDMA NIC product, and this NIC product can be can work together with this UEC ready switch. So I think UEC can reduce the deployment overhead of DCP.
Cool. So David, does that answer your question?
Yes. Thank you. Thank you for the
cool.
answer. So,
thanks.
David. Yeah. If I understand correctly, so basically, the target of DCP is more specifically towards RDMA workloads. Is that correct? I think.
Yeah. DCP's focus is on the RDMA NIC, is the end host part, and the UEC only talk about its packet trimming, the packet trimming function. Yeah.
Okay. All right. Thank you.
So following up on this question, so because I know Wenxue, this paper essentially DCP is a joint work from your group and and Huawei, right? So and we all know that Huawei recently open source its design of its specifications of unified bus. So yeah. my question would be, what's the relation between DCP and the unified bus? Is it already part of the UB, or essentially you guys are working together to see DCP can be implemented as integrated as part of the UB? Well, what's the relation? What's or under the plan?
Actually, I didn't go through the UB specification, but I think currently DCP is not included in the UB specification. And during my intern, I actually prepare a draft for the DCP specification for UV. I'm not sure which distribution or the date it will include DCP into UB. So I think in UB UB consists of two parts: the scale up part and the scale out part. And its scale out part is very similar with UEC. So I think UB's scale out part, UEC, and DCP all work on the same direction. So I think DCP can be part of UB.
I see. Cool. All right. So we are entering the final few minutes of our meeting, but I want to ask a little bit like a relatively non-technical question. So what's like, I know this is a tremendous work. There's a tremendous efforts to finish the DCP. So, but what's the most fundamental challenge or difficulty you run into during designing and implementing DCP? Like, what's the most challenging part to you?
Okay, I think for me personally, the most difficult part is to understand the current RDMA NIC architecture and its ASIC implementation, and to fit the DCP needs to current implementation without very significant modifying overhead, and finally to really implement the DCP design using the FPGA, the Verilog language, and during this process, we can find some unpredicted problem, and we have to solve this implementation problem, and actually we can find some problem we didn't see is a problem when we started this project. For example, the batch prefetching design in the HO based retransmission is a follow-up design. We didn't design it during in the beginning of the project, so it's inspired by the an ideal experimental result. So I think the most difficult part is to do implementation, to evaluate and to find the problem and revisit the design.
I see. Yeah, you are not the first guest of honor to say implementing using Verilog is the most challenging part. I think I forgot. Yeah, you know, different. I think maybe another paper, the author is also from your group. I forgot his name, but he also said, yeah, Verilog is just most challenging part.
Yeah. It's very time consuming.
Yeah. So because our community has been discussing a lot about how large language model can help us, or whether it can help us, or how much it can help us in terms of innovation and research and implementation. So I know like programming in Verilog is very challenging. So have you tried to leverage ask ChatGPT or other or DeepSeek for help during during your implementation or design? What's your experience on that?
I think it will be helpful, but the implementation was done during my intern, and in the company environment, the large language model it's not very reliable. So company will not allow model from other company. So I didn't use very frequently the large language model during this implementation, but I think it will be helpful.
I see. Yeah, I think I think that's probably the attitude for of most of system researchers. I think they think large language model can be beneficial, can be helpful in some time, but probably not right now. But were you at SOSP last week? Did you attend
no.
SOSP last?
No,
me neither. But I think I think last week I met someone who attended SOSP, but he said Xiangzhou essentially his group is trying to use large language model to help improve system design. I didn't attend the talk, so I don't know if there's a slide or a paper about that, but apparently that's what they have been doing, and I'm sure probably not just me, not just you, maybe other people in this meeting or in our committee, they have all been trying to do that, but we'll see how far we can push for that.
Yeah, that's a very cool thing.
Yeah, wonderful. Oh, sorry. We already 2 minutes past our original set. So I assume there's are there additional questions from the audience? Let's give it a couple of seconds. So if there's not, I think I want to thank Wenxue and Qian again for joining us for the wonderful discussion. I think it really clarifies lots of questions we have. And also I want to thank Wenyun for presenting this. Wenyun is only the first year graduate student, and she already I'm not saying she's perfect, but she really did a wonderful job presenting the paper. I think the key ideas are really clean here, and but of course the key ideas itself is very elegant and clean, and all thanks to Wenxue and Kai and all other authors of the paper. So I think with this yeah, thank you. So we can conclude our today's meeting, and we will announce for the schedule for the next few meetings, probably in a week. And so I hope to see many of you in 2 weeks for the next SIGCOMM Paper Reading Group meeting. All right, thank you, thank Wenyun, thank Wenxue, and thank Kai again.
Thank you.
Thank all the participants. Thank you. Have a good night, Wenxue. Thank you.
Bye.